This is a lesson on one-sided limits. So a limit can be approached from the left or from the right. If you approach from the left, you have a little minus sign that you put with it, and if you approach from the right, it's a little plus sign that you see where it's there. Now, here's an example of a one-sided. So the limit as x approaches 2 from the left of this. This is how you would say it. So here 2 is, if you go from the left, the y value is -1. But if you approach the same function from the right side, the y coordinate is +1. So there's a left limit and a right limit. Those are called one-sided. They exist. The actual limit itself does not exist because these would have to equal each other if that limit existed. So the one-sided limit exists, but the limit itself does not. All right, let's just think about it. So it says evaluate the limits for each function that's given. So it says -3 from the left. So that means less than is left, this top piece. And you're just going to evaluate into the function itself because it's continuous. So you're going to go -3, -3, subtract 5. And that's -2. To approach it from the right side, use the bottom function. So greater than is approaching it from the right. Again, we're going to plug -3 in. And get our answer. All right, same thing here. So what's the limit of f at x? Limit as x approaches 0 from the left of f at x. So from the left, it's the top piece. Plug 0 in, and you get the answer 1. The limit as x approaches 0 from the right of f at x. Plug 0 into the bottom piece. Now, these are both examples where only one-sided limits exist. They don't agree, so the limit as x approaches 0 doesn't exist. But if you create a one-sided limit, it does exist. Number 3, 2 from the left compared to -2 from the right. So if you think of this from the right, you would get a positive answer. So if I simplify this, what's the answer going for? Let's look at the graph here. Here, let's look at the graph of what it would look like. So we're looking at this function right at -2. So that's 5x plus 10, and then in the denominator, we have what? X plus 2. So when I look off the graph, I can see that coming from the right side, as you get there, the answer is +5. Now, if I look underneath here, coming from the left, the answer is -5. So I'm looking at the y coordinate. This part here that kind of has a vertical line part, totally ignore it. So there's no answer but -5 here. There's no way, I'm not quite sure why that little hitch is even in there. So it's right there is where it ends. So from the left, the answer is -5, and from the right, the answer is +5, looking off a graph. If I look at number 4, why not? I'm right here. I'm going to graph it. So if I graph number 4, because it's a rational function, I have a negative. It's x plus 2, and then x squared plus x. Subtract 2. So if I'm looking at as x approaches +1, that's where the asymptote is. So at +1, from the left, it's going to infinity, and on the right side, it goes to -infinity. Why not? Look at the next one too. I'll show you my work in a second here. So the next one is x plus 1 and negative x subtract 4. And again, as x approaches negative 4. So if I look here at negative 4, from the left it goes to negative infinity, and on the right it goes to positive infinity. Secant x. Remember what secant x looks like. So what's the value at pi over 2, which is the first asymptote, is at pi over 2. You know what you could do to see it? You can change your scale. Where's the scale here? The step here. And you could change it to pi over 2. And then I think you'll see it better. So it's changed to pi over 2. So what's happening at pi over 2? On the left, it's going to infinity, and on the right, it goes to negative infinity. Let me let you see this. You can see how we wrote it down. So looking off a graph, you can see what's happening on the right and on the left, and then write the answer down. Now, a two-sided limit exists if and only if both the left and the right limit exists. They both have to equal the same answer, then the limit exists. So if you evaluate each one-sided or two-sided limit if it exists. So what's the limit as x approaches 2 for this one? Again, I could go back to the graph to see it. So we'll see it algebraically in a moment too. But if I do this with a graph, so as x approaches 2, I'm going to change this back to 1. There it is. All right. So when you look at it, it actually just looks like a line, right? So at positive 2, from the left and right, they both agree with the answer. So what's the y-coordinate there? So once we get to 2, it's actually a hole. But what's the y-coordinate at that hole? So it's approaching both sides here. And I just want you to see the answer is negative 2. And it exists because the left and the right are both approaching the same y-coordinate. For number 8, might as well, right here, might as well write it in. So it's x squared, subtract x, subtract 6, over 4x plus 4. And so as x approaches negative 1 from the left. So you can see here's negative 1. There's an asymptote there. From the left, it's going to infinity. But from the right, it's going to negative infinity. They go in different directions. They're not approaching the same number, so the limit doesn't exist. But the one-sided limit does exist. Number 9. So number 9 is x cubed plus 4x squared. In the denominator is x cubed, what is it, plus 7x squared plus 12x. And it's as x approaches negative 4. So if you see at negative 4, it does exist. There's no asymptote there. So what's the y-coordinate right there? There's a hole there, but the limit it can exist at a hole. It's removable. What's the y-coordinate it's approaching from both sides? And the answer is positive 4. That's where it is. So we're looking for the y-coordinate. And if the right and the left both are approaching the same y-coordinate, when it gets there, it's a hole, that's fine. That's not what a limit is. It's what it is approaching, not what it equals when it's there. Number 10. So for number 10, we have x squared subtract x, subtract 2, x squared subtract 2x, subtract 3. So the limit as x approaches 3. So if I look at 3, there is an asymptote there. On one side it goes to infinity. On the other side it goes to negative infinity. They don't agree on both sides. They're not approaching the same number. So therefore it does not exist. Number 11, that's x plus 2 over x. So again, I'm looking for approaching 0 only from the left because of the negative sign. So from the left, it goes to negative infinity. The next one, so there's the function for number 12. Again, if you look at it from at positive 1, both the left and the right, they both agree. Both sides, as it's approaching 1, both are going to infinity. So because they agree, the answer is infinity. Number 13. In number 13, it's 2 over 3x cubed. And so what's the limit as x approaches 0 from the right? So from the right, it's going to infinity. The next one, is negative over x to the 5th. So at 0, one side goes up and the other side goes down. So infinity and negative infinity, they don't agree at 0. They're going in two different directions. So the limit doesn't exist. So just so you have the answers for 7 to 14. So I'm going to be working off a graph. So I'm going to go back to this. So we have the absolute value of x subtract 5 over x subtract 5. So what's the limit from the left? So from the left, the answer is negative 1. And if it asked you from the right would be the answer, would be positive 1. Number 16. Again, I'm just going to graph it and look at where the graph is going at that limit. So we have the square root of x, subtract 1, over x subtract 1. And it says, as x approaches 1, what's the answer? So as x approaches 1, there's a hole there, but what's the y coordinate right there? And so the scale here is by a half, just so you know. So that's actually 1/2 right there where 1 is. So the y coordinate's 1/2. Looking off the graph. So again, if you see it this way, you can see that it's at 1/2 right there. That's what the y coordinates that it's approaching. All right, next one. Just type in the graph. One, you can try, always try it first, right? A piecewise, I think you can do this. When x is less than or equal to negative 2, I'm trying to remember how to put in, yeah, there you go, just like that. And then in the second one, you can say f at x equals negative 2x, subtract 1. We could do this algebraically too, but it's interesting looking at the graph. So this one really should be x is less than negative 2. This one is x is greater than or equal to negative 2. So now you have the picture of both. So put them together. And then from the left, the answer is negative 2. And then from the right, the y coordinate, the answer is positive 3. So you can see a jump there. So therefore, and the question actually asked for, just the limit at negative 2. So it doesn't exist for that one. because the left does not agree with the right. They're not approaching the same y-coordinate from the left and from the right. All right, I'm going to stick to this. So I'm going to write the next one. So when I do this piecewise, I'll just write them as two different boxes. So negative 2x subtract 6. Use these fancy parentheses, and then go x is less than negative 3. And then the second one, f at x equals negative x subtract 3. And again, use fancy parentheses. X is greater than or equal to negative 3. Now, what do you notice for this one? So from the left and from the right, do you notice there's no jump there at negative 3? And what's the y value? It's the y-coordinate is the limit. So what's the y-coordinate it's approaching? And the answer is 0. And they both agree that the answer is 0. Number 19. Cotangent 2x Now, if I want to know what's happening at 0, from the left, it's going down when you just look at 0. So if I just zoomed in on 0, so from the left, it's going down. So it's negative infinity. Let me put this back like this. The next one is, these are all trig. I'm just going to graph them and look off the graph, so don't worry about that. Negative 2 cosecant 2x. And I'm looking as x approaches pi. So let me change the scale here. I'm just going to change it to pi so you can see it. So at pi, what's happening? And you can see the left and the right. On one side it goes to infinity, and the other side it goes down to negative infinity. So the limit does not exist. Number 21. It's sine x. So there's your wave for sine x as x approaches pi over 4. So if you can't see it, you can change it to pi over 4 so you can see it. So as x approaches pi over 4, what's the y value there? And at pi over 4, it's actually root 2 over 2. So I don't want you to write it as an answer. Think of your unit circle, but it is root 2 over 2 is the y coordinate there. Here's a fun one. You can write f at x or not equals, and so it's 1 over tangent x subtract 1 and pi over 4. So at pi over 4 for this one, and it says from the right, there's a little plus sign. So from the right, it's going to infinity, looking off the graph. 2 more left. Secant squared subtract 3. So as x approaches pi over 6, so I'm going to change the scale, you got it, to pi over 6 so you can see it. So pi over 6, there it is. So I just zoomed in a little bit. So pi over 6 you can see. So what's the value there at pi over 6? What's the y coordinate? So if you look, it's irrational. At pi over 6 here. What would it say? So f at pi over 6. I wonder if it just give you an answer. So it's negative 1.667. Right there somewhere, right? So that's negative 1 2/3. That was a tricky one. All right, last one. This one looks interesting. So the function is, again, just be able to use a graphing calculator to see a limit. So it's a great skill. So as x approaches 0, so if you look at 0, from the left it goes to infinity, from the right it goes to negative infinity. They don't agree. They're not coming together at 0. They're going in different directions. So that means the limit does not exist. All right, let me show you my work here at the end again. So I forget which question last last with, but there it is to 20 and to 22 and to 24. So you can press pause for what you need. And that's it. Mr. G Math over and out. Till next time.